The size of a rapid population is modeled by the logistic differential equation. He gives that where t is measured in months and p of 0 is 20. What's the limit as t goes to infinity? And what at what value of p does the rate of change reach its maximum? How do we do that? Well, they told us right here that it's a logistic differential equation. So let's go to the notes. Here's the class notes. Two versions of the logistic equation. So I'm gonna grab this one. So dp dt is rp. So let me write that down. So dp dt is rp 1 minus P over K. So that means I need to take this and make it look like that. We do that all the time in math and science. I call it plastic surgery. It's how people think, right, remove the wrinkles, give it a new look, but it's the same person. So I'm trying to take this and make it look like that. Why? Well, because then I can use all these formulas. In fact, I can use the solution. They got the answer there for me. I just need to make it look like this, and then I can read off the solution. So, okay, how do you make it look like that? Well, first off, we got to factor out something, and we got to have a 1 in there. So I got to take this equation, dp dt, and I got to factor out. So there's a 1. Well, that means take out the p over 5, huh? That'll be 1 minus, right? Because p over 5 times 1 will be p over 5. See, I'm making it look like that. And then what goes here, though? Whatever works to go back. It's going to be p over, it's going to be 200 because I know I'll check it on 5 times 200. You can check it on decimals. 5 times 200 will go back to 1,000. P times P will go back to P squared. So I'm giving and one more. Let me do one more step to really make it look like this one does. So I'm going to say, oh, well, that's really 1/5 P, right? Same thing. 1 minus P over 200. Isn't that nice? Now it really looks like this. And you can just say, oh, so this is the R. Right? And this is the K, right? It looks just like this one. I may give it a new look, remove the wrinkles so that it matches this, and then I can tell what R is. I can tell what K is. Okay, why is that so great? Well, now, once I've made it look like this, I can use the solution. There's the solution. There's the answer. So P of T is KP0. So let's write that down. The solution to that differential equation, logistic equation, is what was it? I already forget. KP0, P0, P0 plus K minus P0, and minus P0, e to the minus RT. Okay, so there's our answer. So here, let me get a little room for us. There we go. Okay, so let's plug in the stuff we need for that. Okay, KP0. Well, do we know what K is? Yeah, K is 200. This is 200. This is 200. What's P0? They told her that P0 is 20. P0 is 20. Right there. P0 is 20. What else do we need? Oh, what's R? Oh, we know R. R is 1/5. Or I'll do a different color if it's helpful for you. R is 1/5. Right there, 1/5, which is the same as 0.2. Let's make it 0.2. So then what do we got? We got 200 times 20 over 20 plus 200 minus 20 e to the minus 0.2 t. Yeah. So we can give that one more I guess. This is the solution. So it's at 4,000 over 20 plus what's this? 180 e to the minus 0.2 t. So we got the answer. That's the solution. Now we can take that solution and say, okay, they're saying what is the limit as t goes to infinity of that p of t? So we can figure that out. So the limit as t goes to infinity, like what's going to happen to that population after infinite time? What's the eventual state of that population? as t goes to infinity. So is that making sense? So we have a logistic, we have a rabbit population. Their equation obeys this logistic equation. We gave it a new look so we could grab the solution, wrote down the solution. Now we can let t go to infinity. This is going to be what? 4,000, the bottom, t plus 180 e to the minus point t, and then we'll make t go to infinity, right? 2 times infinity. What is that? Well, that's actually not too hard. That's 4,000 over 20 plus 180 e to the minus, zero point 0.2 times infinity is negative 0.2 times infinity is just negative infinity. So what was that? That is, I'll change color here. 4,000, I'm in the wrong mode there. Making little funny shapes. 4,000 over 20 plus. Now, what do you do with 180 e to the minus infinity? Remember negative powers? Jump to the bottom and then become positive, right? Negative power, jump to the bottom of that fraction. And so that is 4,000, 20 plus 180. What's e to the infinity? E is a number, special 2.718, like pi is a special 3.14 number. E is a special 2.718, blah, 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 blah. To the infinity, that means 2.7 times 2.7 times 2. Well, that's infinity. And so what's that? 20 plus 0, right? 180 divided by billions and trillions is nothing. So this is equal, we're almost there, 4,000 over 20. That 400, half of 400, it's 200. So that means in the long run, that population is going to max out at 200. 200. And that's the answer they got. We could have just looked at the K value and said, well, the K is 200. The K is 200. That's the carrying capacity. That's going to be the maximum population in the long run, right? We could have just done that. It's 200. Once we knew what K was, that took care of it. Now, one other question. At what value of the population does the rate of change reach its maximum? When is it growing the fastest? Well, if you look in the notes, I tell you right here, maximum growth occurs when you're exactly half of your carrying capacity, half a K. So if K right here is 200, that's the total population of rabbits whatever that forest can stand as far as how much food and space and water and stuff they have. Then half of that, 100, is going to be, so when there's 100 rabbits, they're going to be growing, the population is going to be growing the fastest it possibly can. And when they reach 200, that's going to be their max. So if they go beyond 200, they're going to start dying off. So what's going to happen? That's after infinite time, they're going to tend to have a maximum population of 200. But it's going to be growing the fastest. The rate of change is the fastest when they're halfway there at 100. So that's from the notes. And so there we go.